Okay, we're back to probability. This is part 4 of module 4. We have two things left to cover that kind of go together. One is we want to talk a little bit more about marginal probabilities, which we've already looked at, and then there's something called Bayes' theorem. But I'd like to stress that really nothing is new at this point. This is just going to be an extension of things you've already seen. Let's go back to one of these tables. We've been calling the probabilities on the ends of the tables marginal probabilities. For example, the probability of event B here would be this 0.7 down here. Notice what that probability is. It's the sum of these two intersections. B intersects A with probability 0.3. B intersects A complement with probability 0.4. The sum of those two intersections gives us the probability of B. And that's really what a marginal probability is. It's a sum of intersections. We can see this in another way using a Venn diagram. Suppose everything to the left of this line is event A, and everything to the right is a complement. Here's event B, which overlaps both of them. Well, then the probability of B is the sum of two intersections. B intersects A over here on the left side of that line, and B intersects A complement over here. And if you added those two intersections together, you get B. So that's where we're going to start. Let's write an equation here. The probability of B is the sum of two intersections. B intersects A, and B intersects A complement. Now suppose, however, in a given problem, we don't know those intersections. They weren't given to us in the problem. However, other information may have been given to us which allows us to calculate them. If we use the rule of intersections to break down each of these two parts, we can break it down into the following way. B intersect A can be written as A times B given A. B intersect A complement is A complement times B given A complement. And so now we've got the probability of B is the sum of these two sets of probabilities here. It's the probability of A times B given A plus the probability of A complement times B given A complement. By the way, you might realize, remember, an intersection can always be written in two ways, but one of the two ways won't do us any good here. For example, this first intersection could be written as the probability of B times A given B. But the probability of B is the very thing that we're trying to solve for. So that wouldn't have done us any good if we don't know that. So here's just another way of writing a marginal probability. You start with the sum of two intersections, apply the rule of intersections, and you get the formula here. Now let's talk a little bit about what's called Bayes' theorem, or it's sometimes called Bayes' rule. Again, I want to emphasize that in a sense it's nothing new. It's sort of a special case of a conditional probability, but it gets kind of special use in statistics in the way it's the approach that it has and the way in which it's used, as we'll see in a few minutes. In a Bayesian problem, often we begin with prior probabilities. We have some initial probability of some event. Then we get confronted with some new information, possibly from a test market or something of that nature. Then the question is, do we want to revise that probability given this new information? That revised probability is sometimes called the posterior probability. Again, it's just going to be a conditional probability, though. And so you can think of Bayes' theorem as a formula for revising prior beliefs or prior probabilities. Let's develop the formula. Another way of understanding Bayes' theorem in a way is it's going to be a conditional probability where the denominator turns out to be one of those marginal probabilities that we were talking about a minute ago. Let's just start with the probability of A given B. We already know that A given B is A intersect B over B. The probability of A intersect B over the probability of B. Let's suppose that denominator B is a marginal probability that we just looked at a minute ago. That is, the probability of B is the sum of two intersections. B intersect A and B intersect A complement. And as we just did a minute ago, that can be broken down into the probability of A times B given A, plus the probability of A complement times the probability of B given A complement. If you substitute that in the denominator, and also if you apply the rule of intersections to the numerator, you're going to get the following formula. The probability of A given B is equal to the probability of A times the probability of B given A over the probability of A times the probability of B given A plus the probability of A complement times the probability of B given A complement. By the way, I like to use A and A complement in my formula, but some books and some applications of Bayes' rule use A1 and A2 as opposed to A and A complement. Now I know the formula kind of looks big and menacing, but I like to emphasize to students that it's still just a conditional probability where the denominator is a marginal probability. Instead of us knowing what the intersections are, we're going to have to calculate the intersections along the way in a Bayesian problem. As I said, Bayes' rule kind of gets special attention because of the way in which it's used. There's a branch of statistics called decision theory that applies Bayes' theorem. Some of the problems that we talked about earlier, for example, a firm comes out with a new product. They want to know if it's going to be successful or not. They don't have any past data to go by, so they start with some initial prior belief as to the likelihood of it being successful. Then the question is, in the light of new information like a test market, can they revise that prior belief? In fact, we're going to do a problem similar to that in a few minutes. If you know a problem is Bayesian, you can just jump right to this formula. If you don't know it's Bayesian, you can develop the formula along the way, as we did a minute ago. The term in the denominator, the marginal probability, remember, can sometimes have more than two terms to it. This is what I call the n-event case. The denominator could be a sum of more than two intersections. Could be the sum of three or more. We'll never go beyond three, so again, don't get worried about this large, awesome formula here, or impressive-looking formula. But remember, the denominator is a marginal probability, which is a sum of intersections. Most of the time, we only have two intersections, but in a few minutes, we're going to do a problem where we have three. Let's do a problem. Again, probably the best way to understand Bayes' theorem. At a particular college, math and statistics students have the option of using a math lab to help improve their grades. A statistics teacher has found that 70% of her students use the math lab and the rest do not. Out of the students who use the math lab, 90% pass the class. Out of the students who do not use the lab, only 50% pass the class. Given a student has passed her class, what's the probability they used the math lab? Notice the last question that we're given here. Notice that that's a conditional probability. Given a student has passed the class, what's the probability they used the math lab? Again, we should always approach these problems the same way we approach any problem. We need to identify the variables in the problem. Students either use the math lab or not. Two outcomes to that variable. They either pass the class or they don't. Two outcomes to that variable. So let's start setting up some notation. We'll let M be used the math lab. M complementers did not use it. P has passed the course. P complement did not pass it. And now we start to write down all the known probabilities. If you go back to the problem here, 70% of the students use the math lab and the rest don't. So that's just the probability of M and M complement, 0.7 and 0.3. Out of the students who use the math lab, 90% pass the class. You should recognize that as a conditional probability. It's equivalent to saying if they use the math lab, the chance of passing is 0.9 or 90%. So that we have right here. If they use the math lab, the probability of passing is 0.9, and we can write its complement down. If they use the math lab, the chance that they don't pass is only 0.1. Similarly, out of the students who do not use the lab, only 50% pass the class. Again, that's a conditional. If they don't use the lab, the chance of passing is a half. And we have that right down there. Out of the students who do not use the math lab, the probability of passing is only 0.5. The complement to that will also be 0.5, p complement given m complement. By the way, if you look at what we have right here, this is a very typical setup of what will eventually become a Bayesian problem. We have two probabilities, m and m complement, which are actually going to be our prior beliefs. We have an initial prior belief that 70% of the students use the math lab and 30% don't. Those are also, as we'll see in a moment on a table, going to be marginal probabilities. We then have a bunch of conditional probabilities. And eventually the problem is going to ask us for the opposite order conditional. As it says here, given a student has passed the class, what's the probability they use the math lab? So we want this probability right here. Given they've passed, what's the probability that they use the math lab? I still encourage you to draw a table, even though with a Bayesian problem, you don't have a whole lot to put in the table initially. We have our prior probability of m and m complement to be 0.7 and 0.3. We don't know these intersections yet. We were given a lot of conditional probabilities, but remember, they don't go in the table. However, the combination of those conditionals and these marginal probabilities will allow us to figure out all of these intersections. But the table can still kind of help you see what you'll need. Okay, on this problem, I'm going to work it out step by step. If you knew this was a Bayesian problem for sure, you could just jump right to Bayes' rule. You could skip the first step up here and jump to the second. If you're not sure it's Bayesian, it might be a good idea to work it out step by step. As we already said before, we want m given p. That's just a conditional probability, and it has to be equal to the probability of m intersect p over the probability of p. Leave the numerator alone. The denominator is a marginal probability, sum of these two intersections. And this is where the table can help you. The probability of p is going to be this number out here on the margin of the table, the sum of these two intersections. Now apply the rule of intersections to each of these three parts, and you will get the next step here, which is actually Bayes' theorem. M given p is equal to m times p given m over m times p given m plus m complement times p given m complement. If you now look back at your given information, look back at your known probabilities, we have all the probabilities to fill in this equation here. Our prior belief of m was 0.7, p given m was 0.9, and so forth. If you plug all the numbers in and crank out the results, you're going to get a posterior probability or revised probability of 0.807. In other words, while our prior belief that somebody used the math lab was 0.7, knowing that they passed the class, we revised that upward to 0.807. Now, again, I encourage you to study these examples. There is a lot of math involved and a lot of steps. But again, I try to encourage people to realize that if you just work it out step by step, you eventually get to Bayes' formula. As I said a minute ago, if you knew this was Bayesian right from the start, you could just jump to this step right here in the middle. Just jump to Bayes' formula. And do another problem. This is a more typical type of Bayesian problem. This is what I sometimes call a decision theory type problem. A firm has developed a new product. Their initial subjective belief is that the product has a 30% chance of being profitable. They can conduct a test market. The results of the test market is either S for success or S complement for no success. Based on past use of test markers, they found that if a product is eventually successful, the chance the test market indicates success is 0.8. If the product is not profitable, the probability the test market indicates it as a success is 0.3. If a test market indicates success, what's the probability the product will be profitable? Again, identify the variables in the problem. This product is either going to be profitable or it isn't. And the test market is either going to indicate success or no success. So once again, we have a 2 by 2. Let's set up some notation. I'm going to let P be a profitable product and P complement not profitable. S is a successful test market. S complement is not. Again, if you look back at the problem, we have a prior probability of 30% that the product is going to be profitable. So that's probability of P right here of 0.3, and the probability that it's not profitable of 0.7. Then all the remaining given information is going to be conditional probabilities. If a product is profitable, the chance of the test market indicating success is 0.8. That's going to be this probability right here. Given the product is profitable, the chance of a successful test market indication is 0.8. And here we have the complement to it. The probability of S complement given P will have to be 0.2. Finally, the last piece of information, if the product is not profitable, the probability the test market indicates success is 0.3. Given the product is not going to be profitable, the probability of a successful test market is 0.3. And here we have the complement to that, S complement given P complement. Again, be careful in writing down with your notation. Be careful with the complements and all of that. It's easy to make little errors. Notice again, like I pointed out on the last problem, we have setup of a Bayesian type problem. Several conditional probabilities and our initial prior probabilities. Again, we have very little that can go in the table, just our initial prior probabilities. The probability of a profitable product initially is 0.3 and not profitable is 0.7. But along the way, we're going to fill in these intersections. Once again, what is it that we want to find? If the test market indicates success, in other words, given success, what's the probability the product will be profitable? So we want the probability of profitable given success. Now this time I'm just going to jump straight to Bayes' formula rather than write out all the intermediate steps. As I said, if you realize it's Bayesian, you can just jump straight to this formula. The probability of P given S is going to be the probability of P times S given P. In the denominator, we have the probability of P times S given P and P complement times S given P complement. Plug in all the numbers from your given information. Your prior belief of P was 0.3, S given P was 0.8, etc. Do the calculations carefully and you will come up with a final answer here of 0.533. Given a successful test market, this means that we've raised our prior probability of a profitable product from 0.3 up to now 0.533. Finally, we're going to do one more Bayesian type problem. So far, most of the probability problems that we've done, in fact, I think all of them, have been 2 by 2 cases. You had two variables and each variable had two outcomes. Every now and then, I'll go to 3 outcomes for a variable. I don't like to go more than 3 because the formulas just get bigger and the tables get bigger. But let's do what I'm going to call a 2 by 3 problem. consider a professor who only gives A's, B's, and C's on exams, which is not me, by the way. But I'd love to see everybody get A's, B's, or C's. From past experience, the professor has noted the following. 10% of the students get A's, 30% B's, and the rest C's. Out of the students who get A's, 90% study. Out of the B's, 70% study. And out of the C's, 50% study. Now this time I'm going to ask you two questions. I'm going to break the question into two parts. What is the probability a student studies? And if a student studies, what's the probability they get an A? Again, identify your variables. You'll notice what's different about this problem is one of the variables, your grade, has three alternatives to it, A, B, and C. The other variable is whether you studied or not, two alternatives. So here we're going to have a 2 by 3, as we'll see when we draw a table in a minute. I'm going to let A be a grade of A, B be a grade of B, C be a grade of C. You could have used a different notation than that if you wanted to. You just need to realize that each one of those is the complement of the other two. S will stand for studying, S complement not studying. Look back at our given information. 10% get A's, 30% get B's, and the remaining 60% get C's. So those are just going to be right here the probabilities of A's, B's, and C's. 0.1, 0.3, and 0.6. Again, the rest of the information in the problem is conditional probabilities. Out of the students who get A's, 90% study. So that means right here, given an A student, given somebody who gets an A, the probability they study is 0.9. And if you want, again, you can write down the complement to that. You might not need it in the problem, but we can put it down. S complement given A has to be 0.1. Similarly, out of the B students, 70% study. So given they're a B student or given they're going to get a B, the probability of studying is 0.7, and its complement. S complement given B is 0.3. And finally, out of the C students, 50% study. Again, when you say out of this or among this group, that indicates a conditional probability. You're restricting yourself to just that group. So that's equivalent to saying if they get a C, the probability of studying is a half, and its complement. The probability of S complement given C is also a half. Again, notice we have several conditional probabilities, and we have one set of marginal probabilities. If we draw a table now, we have a 2 by 3 table. A, B, C, we have three outcomes to the grade, so I have three columns set up for the grades. I was able to put in the marginal probabilities we were given for those, and the other variable is study or not study. Once again, initially I do not have these intersections here, but we're going to figure them out along the way. Now notice what we want to find first. And like I said, I changed this problem around from what we did before. What's the probability a student studies? If you look at your table, you should be able to see the kind of probability we want. The probability of studying, S, is going to be out here. It's a marginal probability on the border of the table. Notice that that's the sum of three intersections. S intersect A, S intersect B, and S intersect C. So I'm going to write this as the sum of three intersections. The probability of S is equal to S intersect A, B, and C there across the top. Apply the rule of intersections to each of those three parts, and you'll get what's on the second line there. S is equal to A times S given A, plus the probability of B times the probability of S given B, plus the probability of C times the probability of S given C. If you go back to your given information now, you have all of that. The probability of A was 0.1, S given A was 0.9, and so forth. And you've just calculated the three intersections here. 0.09 plus 0.21 plus 0.3, and the answer is 0.6. If I went back to my table, I could fill in these three intersections with the 0.09, 0.21, and 0.3, and they will add up to 0.6. Now, part B, as it turns out, we've actually done all the work to make part B pretty easy. Part B, if a student studies, what's the probability they get an A? If this, the chance of something else, is again a conditional statement, a conditional probability. So we want, given S, given they study, what's the probability of getting an A? Given S, what's the probability of A? Let's just apply our basic rule of conditionals. That has to be the probability of A intersect S over S. But we've calculated both of these now. Part A of the problem calculated the probability of S as 0.6, and the numerator A intersect S was the first term here, 0.09. So we already have everything that we need to finalize this answer. 0.09 over 0.6 is equal to 0.15. By doing the marginal probability first, we really figured out both the numerator and denominator of part B, and we didn't actually have to use Bayes' formula per se. Okay, I never go bigger than 2 by 3s, so I think if you study these last three examples, you'll have a good idea of how to apply Bayes' theorem. Okay, at the very end of this section, I threw in a couple of famous probability problems. These are just for fun. We're not going to do them now. I might actually put one of these in a discussion question. You don't have to worry about solving problems like this on tests or anything like that, but just fun problems. Imagine 3 boxes. Each box has 2 drawers. One of the boxes has a gold coin in each drawer. One of the boxes has a silver coin in each drawer. One of the boxes has a gold coin in one of the drawers and a silver coin in the other. We randomly pick a box and we open one of its drawers. We see a gold coin. What's the probability that the other drawer in this box has a silver coin? I believe this is referred to as Bertrand's box paradox, named for, I assume, somebody called Bertrand. See if you come up with an initial answer to this question. Think about it. And see what you come up with. And we'll possibly give you answers to these later on. Again, these are just for fun. Here's a second one. Actual historical problem. The Grand Duke of Tuscany liked to play a game where he rolled 3 dice, and he added up the numbers. He was perplexed with the following problem. He thought there were 6 triplets that would give him a sum of 9, namely 1, 2, 6, 1, 3, 5, 1, 4, 4, etc. And he thought there were also 6 triplets that would give him a sum of 10, 1, 3, 6, 1, 4, 5, and so forth. But he played the game enough that he knew that a sum of 10 seemed to have a higher likelihood of happening than a sum of 9. And he supposedly ordered his official court mathematician, who was a person by the name of Galileo, that you probably remember in your science classes somewhere. And Galileo was supposed to solve this problem for him. Can you figure out the solution? Finally, one last famous problem, the birthday problem. Suppose your classroom has 30 people in it. Assume they represent a random selection of the population. Intuitively, what do you think is the probability that at least 2 people in the room have the same birthday? That is the same month and day, but not necessarily the same year. Would you expect the answer to be greater or less than 50%? Think about that one for a while. And I may make another video later to talk about the answers to these, or as I said, I might put them in a discussion question. So have fun with those. And that is the end of this module.